So I'm Pranjal Jain. I'm a fifth year BSMS math student, and my master's thesis is in algebraic topology. And today's talk is somewhat related to, like, it's within that area. It's on the Hairy Ball Theorem. So I'm sure you guys must have heard like some layman conception of what the theorem is. And basically what it says is that if you have a hairy ball, by which I mean, so right now when I say in the layman term ball, I mean S2, which is the two sphere. So it's the set of all x, y, z, or maybe let me say x in R3 with norm x equal to 1. So if you have a two sphere with hair on it, which basically means that like you can imagine hair sticking out of it, you can't comb it. And at first that sounds a bit nonsensical, because like if you have finitely many hair, you can just like if you zoom in enough, you can just take each one individually and put it down, right? So what we mean by a hairy ball in this case is it's a more like continuous distribution of hair. So to formalize this setup, one thing you could do is view each hair as a vector. So you have a sphere, and to each point you associate a vector which is just pointing radially outward, and this is your initial configuration. So each point has a vector sticking out of it, and you want to sort of take this and put it down in a continuous manner. So this hair could maybe go down like that, and then some hair close to it has to follow a trajectory which is nearby, so that the whole thing is continuous. So we want we have something like an initial function from S2 to R3, which just takes each point x here to the vector x. So here this x is to be thought of as a point on the sphere, and this x is to be thought of as the hair sticking out at that point. And you want to sort of continuously take this to another function which takes S2 to R3, and this is like the initial state with the hair sticking out, and this is the what I'll call the combed state. So what I mean by that is each hair should end up in like tangent to the sphere at this point, and it starts with length 1, so it should stay length 1. So like you are basically taking the hair and putting it down. So here the conditions on F1 which you would like to put are that F1 of x, the length is 1, and F1 of x is perpendicular to x, or like if you like linear algebra, then you could say F1 of x and x have an inner product 0. So something like that, and like a process of combing would basically look like taking a hair from the initial state to the final state. So I think it's sort of obvious that if I tell you that there exists a final state, like a combed state, then there will always also be a process to bring it into that combed state, right? Like if this is the initial state and this is the final state, you can always just rotate it, and like if the final state is continuous, so F1 is continuous, then this whole process will also be continuous. And I'm being a bit vague, but I guess you can see what I mean. So basically the problem reduces to whether we can find such a function F1, and since we are just talking about one function, might as well just drop that one subscript. So we want to ask, does there exist a function f from S2 to R3 satisfying these properties? So how do we proceed with this? So one thing you could think about is here, like your the output of f is quite restricted, right? For every x you want to satisfy these conditions, and geometrically what that basically looks like is for any point x, there is like a tangent circle around this point, like it's in the plane tangent to the sphere at this point, and it consists of unit vectors. So you want, so if this is x, then you want f of x to be something like this, right? So again, I want to make this distinction that x is like a point and f of x is like a direction. So I want to think of f of x as a vector originating here and going to some point in this circle. So the image of any point, so if I fix some x in S2, then the image f of x should lie in a certain circle, and S1 here just means the circle. So like similar to S2, S1 is the sphere in 2 dimensions. So yeah.
So you want that vector to be in the tangent plane of that point?
Not just the tangent plane, but also of unit length. Yeah, that's why I'm getting a circle and not a plane. So this certain S1 varies with every x, right? It's not just, so I don't want a map just from S2 to S1. That won't work, because this the circle in question is different for every point. So how do you sort of encode this? So like certainly this codomain of R3 is a bit too big for a function which is so restricted. So can we sort of or rather, instead of refining, I would say, can you bake these restrictions into the codomain of f itself? So at first, as I said over there, it seems a bit tricky because this circle is changing for every point. So you don't just want to map from S2 to S1. So one thing you could try to do is think of taking a map from S2 to S2 cross R3, and or maybe let me say B, which is a subset of S2 cross R3. And what this B is doing is that the if I take any point x in S2 and look at this cross R3 intersection B, so this is like one slice of B, that should be so this space should be the certain S1 that I mentioned over there. So for each point x, the intersection of this B with like the R3 corresponding to that x will be this circle. And so what we want now is, so a map similar to f would look like, maybe let me call it f tilde. So yeah, so f tilde should satisfy the property that like you'll have two coordinates, since it's going into something with two coordinates, and f1 tilde should just be the identity on S2, right? So basically I'm sort of adding some information of like I'm adding an extra coordinate, but it's just like a trivial coordinate. It's just the identity map on that coordinate. And in the second coordinate, I'm baking in the restrictions which I want over here. So over here we were asking for a function S2 from S2 to R3 which satisfies certain properties. But here you can just take any old map from S2 to B, which whose first coordinate is sort of trivial, and that will work, right? So this makes sense, right? That if I have an f tilde like this, I can construct an f like this. So another way to frame this condition of the first coordinate being identity is that you take the map from here to S2, which I'll call P, which is just the projection onto the first coordinate. So I want to say that if I apply f tilde and then I apply p, so maybe let me draw this in draw a few arrows. You have S2 going to B, which is this is f tilde. So I want this whole composition to be identity. So this is what we want to find, or rather let me say this is what we want to probe, like whether such a function can exist or not.
So by B means that the circle you mean, or like a
No, so B is a subset of S2 cross R3, and I'm trying to bake in those conditions which I mentioned before, right? So think of it like this. For each point x in S2, B has a corresponding circle in it, right? So not this one, this is the equatorial. This circle, which is like tangent to that the sphere at that point. So think of B as carrying, like for each point S2 you in x in S2 you give me, B will have that circle sitting inside it. So you can, so this circle is basically so this circle is basically just P inverse of x, right, in terms of this projection map P, right? So that's what I said over here, that this x cross R3 intersection B should be that certain S1 which I mentioned previously, which is like tangent to S2 at that point. So now to find such a function, we can make some naive guesses, right? So from the initial idea of like combing the hair on a ball, you might think of sort of sliding your comb. So like you have hair sticking out of this sphere and you slide your comb like this. So on, I guess, latitude circles. So if you do that, then as you approach this point, these hairs will be like going around, right? And they're all of length 1. So over here the continuity will break, because close to this point you have hair which is pointing in all sorts of directions. So no matter where I put down this hair, there will always be something nearby which disagrees with it, which is basically violating what we understand by continuity. And likewise, similar thing would happen on the South Pole. So this certainly doesn't work. Another thing, so this idea was coming from our combing intuition. Another coming from this formulation might be that, okay, you have a north pole which I'll call nu and a south pole sigma. You just set down the hair at nu in any direction you like, okay, and then you start combing downwards like this. So the hair over here will go down like that, over here it will go down like that. Now these hairs will go down like that, right, and so on. So I'm sort of what's called parallel transporting this direction down. So think of it as like I have my finger pointing like this on top of the sphere and I'm just moving it down in all sorts of directions. So that is like how I'm combing it. And of course you could continue doing this all the way to the South Pole. But then again you face a similar sort of problem, that once you reach the South Pole, near the South Pole you have hair pointing in all sorts of directions. So no matter where you put down the South Pole hair, you will always have some discontinuity. So these naive attempts tend to fail, and that is why this problem is interesting, that like can such a function even exist? So how do we work with this problem? So one thing you might think of is, since each point is essentially mapping to a certain circle, you could just look at a map from S2 to S1 and then identify this S1 with these certain circles for each point, right? So ultimately it's just a circle, so you can just identify it, right? But then the problem with that is you need to have a continuous identification. So it's not so straightforward basically. But there is something to this idea, because what you could do is this B, to understand this B, you could try to take this identification idea as far as possible. So let me establish some notation now, I guess. I'll say Hn for the northern hemisphere, and of S2, and likewise Hs for the southern. And now what you could do is you could try mimicking this idea. So what you do is this, like the circle corresponding to this nu, that is easy to identify with a usual circle sitting in the plane, right? Because it's just parallel to the circle sitting over here. Just move everything down. So maybe you could try something similar, that you think of sliding this circle down, and that will give you an identification of, say, the circle corresponding to this point with S1, the circle corresponding to this point with S1, and so on. And you stop doing that at the equator. So what I'm trying to do is taking Hn cross S1, by which I mean that for each point in the northern hemisphere, I have a copy of S1, and I'm taking this to let me say P inverse of Hn, which is sitting inside B. So inside P inverse of Hn, all these circles are like tilted, right? For each point there's a tilted circle associated to it. I'm sort of straightening it out by doing this sort of thing. And this map is given basically by the sliding action, that the place where like if I take some x in Hn and let's say some z in S1, where z comes from complex numbers, circle in the complex plane, that will map to x comma whatever you get by sliding z down to x. So I'll write that again. I'm not trying to be formal. And you stop doing this at the equator, and then for the southern hemisphere, what you do is you start with a circle on the south pole and slide it up. Same sort of thing. So any questions so far? So this sliding idea is fine, right? That like I'm associating these directions with the corresponding directions over here by just sliding down this vector. But the thing that now happens is, if you look at the equatorial circle, then over there, so maybe let me draw a new diagram. It's getting a bit messy. Okay. So if I look at a point on the equator, and let's say I pick this vector which is coming out of the board, so I'm drawing it downwards but it's coming out of the board. If I slide it down, it will then actually become straight downwards, right? And if I do this, a similar thing over here, again start with a vector which is pointing out of the board, so this and this are actually parallel, you will get a vector pointing upwards. So these two identifications are disagreeing with each other on the equator. So to counter this, we can sort of glue these two so that these vectors start to correspond. So what I mean by that is this upper hemisphere is basically just a disk, right? It's a two-dimensional disk. So that is what we call D2. So D2 cross S1, if I take a disk and just rotate it, I get a donut, right? A solid torus. So this is actually just a solid torus. And likewise for the southern hemisphere. And what I'm saying is B is composed of these two solid tori. So like there are two donuts which are sitting inside B, and their intersection is basically this equatorial circle together with all the circles corresponding to each point on the equator. So basically they intersect on S1 cross S1, which is like the surface of a donut. So you're taking two solid tori and you're gluing them on along their surfaces in some manner, and what you get by doing that is B. So how do you glue those? So before we go into that, let me recall a slightly simpler example of this gluing process, which I'm sure you must have seen animations of.
One thing I want like
Yeah.
you are just parallel transporting every vector to equator.
Yeah, exactly. So I'm actually parallel transporting it to everything on the upper hemisphere, but the equator is particularly special because that is where you have an intersection of these two guys and you want to see whether they agree or not. So to go into this gluing business, let me talk a bit about how you get a torus by gluing the sides of a square. So you take a sheet of paper and glue these opposite edges together and you get an annulus, or you can think of it as a cylinder without the base and the top. And then you glue this bottom circle to the top circle to get a torus. So how do you think about this gluing process? You basically have, like, you want to build a correspondence, right? If I have a point over here, I want to say that glue this point to this point to this point, and so on, right? That is basically what I'm doing when I'm saying I'm gluing these two things. So basically I can talk about a map from this circle to this circle, and the gluing is happening along that map. So this point, that map will take to this point, so these two are glued. This point will go to this point, so these two are glued, and so on. So can we do a similar thing in our setup where you have these solid tori which you want to glue along their boundaries? So maybe I will call the equator as E. This is very non-standard notation, but so E cross S1 is sitting inside this, and it's also sitting inside that. And basically what I want is a map gamma from, okay, actually let me say En for, so I'm taking like a disjoint union, so I want to distinguish between these two. So let me say En for like when I want to talk about the equator specifically sitting inside the northern hemisphere, and likewise ES. So I want something from En cross S1 to ES cross S1. So just to recap where we are right now, this coordinate refers to the points on the sphere, right? And this coordinate refers to direction. So if this coordinate is equal to say this point on the equator, this S1 will look something like that. So it will be a circle which is tangent to S2 at that point, or rather it lies in the plane which is tangent to S2 at that point. So this map, so what I'm saying is that if we find this map, then B will basically be, you take the northern hemisphere and disjoint union with the southern hemisphere, and you mod out by the relation, the gluing, which takes x comma z, which relates this with gamma of x comma z, where this thing is thought of as lying inside En cross S1, and this thing is thought of as lying inside Es cross S1. So let me say homeomorphic. So this is the sort of thing we are going for. And again, why is this important? Because B is the codomain of our map F tilde. So you will see how all of this comes together in a very nice way soon. So any questions so far?
So like En cross S1 is just like a boundary for Hn cross S1.
Exactly, yeah. So yeah, I said that these two are solid tori, but it doesn't really help to visualize them as donuts, because then understanding what each coordinate represents becomes a bit hard. So I want you to continue thinking of it as going to some point on the sphere, possibly in the northern hemisphere, and looking at the corresponding circle.
And also
Yep.
like you identified x comma z to the gamma of x comma z, which
Mhm.
is just you are just identifying two torus only, like
Yeah.
bit of identity map.
Yeah. So no, it's not the identity map.
No, it's like they are same. They are
Yeah, like they are homeomorphic. Gamma will be a homeomorphism, but yeah, it's not the identity.
okay.
So yeah, in the example, so going back to the gluing of sides of a square, if I glue them the same way, I get the usual cylinder. But there is also a more interesting way of doing it, where I glue them in the opposite directions, right? And then what I get is called a Mobius band. So the gluing maps in these two cases are different, and the spaces they are giving me are also quite different. So the gluing map matters a lot, and in our case, you will see it's not the identity. So how do we find this gamma? It basically boils down to this sort of thing which I was talking about, where you take basically the same vector pointing out from the board, slide it to the equator from the south pole and from the north pole, and see how they match up. So if I take so let's say you fix a point on the equator, some point x, or maybe let me take this one. And let's take this again, the same thing, the vector coming out of the board here. Maybe I'll do this one in a different color. vector coming out of the board over here. And now this vector is basically like, if I think about, and this x is also like the point which is towards us in the like closest to us on the sphere. So this point is, this direction is basically the same as x, right? If I take the origin, draw the vector from 0 to x, that's basically the same thing, straight out of the board. So what I'm doing is I am looking at where gamma takes x comma x, right? So this downward vector which I get, after sliding this down, the downward vector I get actually corresponds to x in this, erase that. So where do I draw it? Let me see here. So you had something like this, d2. So under this identification, which we didn't write out explicitly but I described as the sliding action, this downward vector at x corresponds to the vector coming straight out of the board. So that is basically like, you go to x, which is the point, and then you look at the direction, which is x. So it's something like that, and that is being and that is supposed to be the same as what I get after sliding this up. So that's basically x comma minus x. So I can color code these, I guess. Yeah. So you have this relation. So at least as you vary x around, so I just gave you one example where x is the point closest to us on the sphere, but you could also take some point over here, right?
So point is on equator.
Yeah, x is on the equator.
We are not distinguishing between it's on HN or SN, HS.
So basically what I want to do is look at how this circle, which is like vertical, is being identified with like the usual circle on the two-dimensional plane. So you are getting two different identifications, right? If I view x as lying in the northern hemisphere, then I'm sliding from the north pole, and I'm getting some identification, and from here I'm getting some different identification. So that's what's going on.
Okay, so in that point, and what's the direction? Like we get two directions. Like one is coming from the north, north pole that was pointing down, and while coming down, it's pointed down.
Yeah.
So that x direction is down only, right?
Yeah.
Pink x. Okay.
Yeah. So and if I had taken x, so let me say y, if y is not this point which is like closest to us on the sphere, the same equation will hold, because then the vector corresponding to y will be something like this, and you're sliding it down like this, you get something pointing straight down, and over here you slide this to y, you get something pointing straight up. So you still get this relation, right? But now for each x, there are still many directions left to think about. So how do we figure that out? So now you could fix x, and instead of sliding down the vector which is pointing straight out of the board, I could take something which is slightly rotated from this direction by, let's say, some angle theta. So this is counterclockwise rotation, right? So when I slide it down to x, I will have something counterclockwise rotated by the same angle. But if I try to do something similar from the south pole, I start with again something rotated by theta in the counterclockwise direction. So this is a bit confusing to visualize, but basically think of this dotted line as being straight out. So I am rotating it counterclockwise, and when you reach over here, you will have rotated it like this. Does that make sense? So think about it, like I have this straight out direction, I take something at an angle and I slide it down. So that is the pink thing which I am getting, and I take the same thing and slide it up. I get basically its complex conjugate in some sense, right? It's rotated in, so it's not exactly the complex conjugate you are working in 3 dimensions, but it's something like that, that it's rotated in the opposite direction.
In the tangent plane it will be.
Yeah, exactly. Yeah, in the tangent plane they will be complex conjugates. So what this is suggesting, again I'm hand waving a bit, but obviously this can be made precise, is that if I take the point x, at the point x, I take the direction x times e to the I theta, then this is coming out to be x comma minus x times e to the minus I theta. So this minus is like basically you're flipping the direction and you're also changing the direction of rotation, so that's why this minus. So this is basically what gamma is, and we have found it in a precise way. Like when I say precise way, I mean the expression is precise, the derivation wasn't that precise. So you can now start thinking of both coordinates as complex numbers, and let's say for ease of notation call them uv. So what you're saying is gamma of uv is, now x is u, so this is minus u times this is basically v by u inverse. Make sense? So simplifying, you have u square v inverse, and if you like thinking in terms of angles, then I can say gamma of e to the I theta e to the I phi is e to the I theta comma, so this will become 2 theta minus phi and then plus pi for the minus sign, something like that. So this is what gamma is, and again why was gamma important? You had these 2 solid tori which were the northern hemisphere with each point associated with a circle and the southern hemisphere with each point associated with a circle, and you want to glue them along the boundaries, and this is your gluing map. So think about this for a moment. It's a bit like you can't really visualize this in 3 dimensions. So you have these 2 solid tori and I want to glue them together with this weird mapping. It is quite interesting to think about, like how far can you visualize this, but I won't go into that right now. So what can I erase? Let's see. Maybe let me go with this. So now we can come back to our goal of understanding whether such an f tilde can exist. So since I have this nice identification of B with this kind of a space, what I can do is I can say f tilde is equal to something like f1 tilde, x is in Hn and f2 tilde for x in Hs. So I'm identifying B with this and I'm defining f in this piecewise way. So the sphere is the union of these two hemispheres. So on the northern hemisphere I do some f1 tilde, on the southern hemisphere I do some f2 tilde, and this f1x f1 tilde x will have its own two components, right? So if you go back to what f1 tilde is, it's something from Hn to Hn cross S1 with the first coordinate being the identity, right? And likewise f2 tilde southern hemisphere to southern hemisphere cross S1 with first coordinate identity. But of course the domains of definition of f1 and f2 intersect, right? So if I want them to agree and define a proper function of on all of S2, they should agree on the equator. So what would agreement on the equator look like? You would, so any guesses for that? What would agreement on the equator look like?
F1 of some point at the boundary
Mm-hmm.
would be equal to F2 of the corresponding point at the other boundary. F1 tilde.
So you are saying this for x in E.
That in E.
Okay, any other answers? So remember that these two solid tori, they are not like, again we go back to the square example. If I was talking about the Mobius band, then like I want to define, so this whole thing after gluing is the Mobius band. I want to define a function from the Mobius band to some x. Then the condition I would want to impose is that some like whatever this point goes to is the same thing which this point goes to, right? Because I'm doing that twist while gluing. So I need to look at the gluing map as well. So this point will go to the same point that the corresponding glued point goes to. So what is the, so if this x is thought to be in En, then what is the corresponding glued point? It's gamma of x, right? So yeah. So here like you have things happening in the domain. Maybe let me state it this way. So here our situation is the opposite, my bad. You are taking some map into M, right? So if x is taking something to this point, then it should also take that same thing to the glued point. So basically what you have is gamma applied to F2, or maybe the way I set things up, it will be this. Yeah. So whether gamma goes on that side or this side, you need to think through a little bit based on how we have defined things. So what I wrote here, I don't know why I keep erasing things which I need. Gamma was from Hn. Let me see if I can make it out. Okay, I can't. So I guess I'll just go from memory. So this was what gamma was. So gamma will be applied on the thing in the northern hemisphere. So this is the condition we have. And now of course f1 tilde will have two components, right? The codomain has two components. So we can look at those components individually. We have an explicit formula for gamma. So that should help out. Maybe let me just keep this thing. So what will f1 tilde look like? It will have first coordinate identity, and the second coordinate will be something unknown. So let's call that, I don't know, g1 maybe. So you are applying gamma to this thing, where g1 will now be a map from hn to s1. And we know exactly what you get after applying gamma to such a thing. You get x comma minus x square g1x inverse coming from that formula. And this f2x will again have a similar decomposition. So this is supposed to equal f2 tilde of x. So I can write that as x comma some g2 of x, where g2 is from hs to s1. So you have something like this.
Wasn't gamma from En to Es? Like, what was the function from En cross S1 to?
Oh, right. Yeah, sorry. My bad.
Right?
Yeah, nice catch. Thanks. So, yeah. So, this is what you get. And now you can start. So, the first coordinate is not very interesting. It's just identity in both things. So, let's focus on the second one. So, the equation you get, maybe let me put this in color, is minus x square g1 is equal to and another way to think of it, sorry, g1 inverse. So you have this. And now recall that x is on a circle, right? E is just a circle, it's the equatorial circle. So think of it like this. So you have E, when x goes around the circle once, the left hand side goes around twice, right? The squaring map. And this thing we don't quite know, but we have the equality. So this g1x will basically, okay, how do I frame this? So g1x is, yeah, sorry, here also I should have en and es. Yeah, so g1 is from circle to circle. I can ask how many times does it go around, what's called a winding number, right? So the winding number of a map from one circle to another is basically just you look at how many times does it go around the circle. So if you've done complex analysis or maybe algebraic topology, you will be familiar with the more rigorous theory of this kind of a thing. So G1 will have some winding number of how many times it goes around. G2 will also have its own winding number, and when you multiply two things, the winding numbers add up. So if you're interested in why, maybe we can take this at the end of the talk. But basically this one will go around some n1 number of times, this will go around some n2 number of times, and what you're saying is that the sum is 2 because this thing goes around twice. So by the way, these are integers because I'm taking into account the direction as well. So if I go counterclockwise, that's 1 rotation. If I go counterclockwise, that's counterclockwise is 1 rotation, clockwise is minus 1 rotation. So taking winding numbers on both sides, the sum is 2. So in particular, at least one of these has to be non-zero, right? That's the simplest conclusion you can draw. And that, I say, is the contradiction to such a function existing, because this this G1, which is a map from a circle to a circle, can be extended to the whole northern hemisphere. So what I mean by that is, okay, yeah, actually this should have been H. So yeah, maybe let me recap what's going on over here. So this F1 is like, it has domain Hn and codomain Hn. So like G1 was just the first coordinate of F1. So where there, yeah. So
the
yeah, maybe
analysis on right hand side is just hand wave analysis, that the hand wave analysis of rotation,
mm-hmm.
n1 plus n2, like G1 and G2 will give some notion of rotation, and that
Yeah.
the addition should be 2.
Yeah.
But how it is contradicting something?
Yeah, I haven't told you why it's a contradiction yet. So this is G1x and x comma G2x. So this G1 can actually be extended to the whole 2 disk, right? Here we are just talking about what it does to this circle, but it can be extended to the whole disk. And when you extend it to a disk, you are saying that, so think about this, you have a map from S1 to S1, it's going around some number of times. If you extend this map to a disk, so what I mean by that is, you have circle to circle, and then I extend that to a solid disk to S1. That means that the map on the boundary must have winding number 0, because you are taking this circle which is going around some number of times, and then you can contract it, right? So if you can, so imagine this, if you're going around once, I have a rubber band which is going around this once, and I can slide that rubber band down to a point while staying within the circle. That can't happen, right? That must mean that the rubber band sort of maybe goes something like this and then comes back, right? That is the only case where you can slide it down. So again, I'm being hand wavy, but this is basically the theory of finding numbers.
You are mapping all the circles, like there will be many circles on the disk, and you are
yeah, the
mapping all
small, yeah.
one big sphere, so you are expanding some small circles and mapping it. And so what's the problem here?
So this boundary circle, it has to have winding number 0 over here,
Doesn't the winding number 0 then?
because then you can't extend it to the whole disk, because you are contracting, like you can, so think of it like this, you have many maps from S1 to S1, where, like sitting inside this map from disk to S1, and in the center you have a map, like a single point, right? So let's say that point is going over here. So what you're saying is, let's say this circle is going around once, so you have this, and then you're changing it like continuously into another circle, so that the whole thing ends up over here. But you're also staying within this circle the whole time. You're not, like the disk, the interior is not there. You're on the circle, right? So that can't happen. Yeah. No, you need a simply connectedness argument. So basically what I'm saying is that pi 1 of S1 is Z. That's what's going on.
I was saying that here does not exist any continuous map from disk to circle. The image is the circle, full circle.
No, so what I'm saying is, you cannot have a map from D2 to S1 such that the winding number of the boundary is anything other than 0. So yeah, basically pi 1 S1 is Z. So yeah, so that would means that since G1 can be extended to a disk, G2 can be extended to a disk, the winding number of both these guys has to be 0. N1 and N2 are both 0, but then they can't possibly add up to 2. So that's basically the contradiction. So this thing about winding numbers, maybe I can go a bit more in depth into that. Would you like me to? Yeah. Okay. So yeah, as far like if you agree with me that winding numbers, firstly winding numbers add up when you multiply two things, and secondly you can't have winding number non-zero if your function can be extended to a disk. If you agree with these two things, then the proof is complete, right? So I won't give a proof of these two things, but maybe I'll give a rough idea which can be made into a proof. So think of a map from S1 to S1 as a map from the interval to S1. So basically what I'm doing is I'm unwrapping the circle, which looks like this. I fix a point and I unwrap it and I get the interval 0, 1. So there is a correspondence between these maps such that 0 and 1 map to the same thing over here, right? So that you can glue it up. So let me call this gamma because it's a path. And now I can, what I can do is, let's say this 0 and 1 are actually mapping to a specific chosen point on the circle, let's call it P. So what I can do is, like when I start at 0, I am starting at P, and then when I start traveling along this interval, I'll go somewhere on the circle based on what gamma is, right? So let's say initially I start going like this, then maybe I go back a little bit, go forward twice, something like this. It could be a mess. So what I could do is, throughout this process, keep track of what angle I am at. So initially I start at some angle, let's say theta of the x-axis. Then I go a little bit forward, so theta increases. Then I go back, so it starts decreasing and I end up with a negative angle. Then when I go around twice, my angle jumps up to something like 4 pi, right, or 4 pi plus theta, and so on. So ultimately I will land up back at P somehow. So the total angle which I have covered this has to be something like 2 pi n, where n is an integer, same, just because I'm landing up at the same point after the whole thing is done. So this is basically the winding number. This n is the winding number of my map from S1 to S1, which I first opened up to a map from interval to S1, and then I kept track of the angle. So this is the winding number. Again, it has to be an integer, but it can be negative as well, right? Because if I was just going around clockwise, then this would come out to be negative. So now it's sort of obvious that if I have two functions, gamma 1 and gamma 2, with let's say gamma 1 satisfying this, gamma 2 satisfying something else, so I multiply them, gamma 1, gamma 2 of 0, gamma 1, gamma 2 of 1, this will be P1, P2. So basically what I'll be doing is I start at some other point P1, P2, do the same thing, keep track of angles and get some integer out at the end. So now it's sort of obvious that when I multiply two things, the total angle covered will add, because multiplication on like the complex circle is just addition of angles, right? So if I'm keeping track of two things separately and then adding it, or first adding and then keeping track, it will give me the same thing. So that basically explains this side, that why is the winding number of the product the sum of the two winding numbers. Now the second thing is slightly more complicated, but we can see that nonetheless. So for the second thing, we have a map from the 2 disk, which is like the disk in the complex, unit disk in the complex plane. Let me say capital F, and like you have what I'll call del F, which is just the restriction of F to S1. And we want to study the winding number of del F. So how do you find the winding number? First you unwrap it to, let's say, some gamma from 0, 1 to S1, and then you keep track of angles, right? So let me call this gamma 0, and okay, wait. I'll need to modify the notation a little bit. So let me think of the disk as made up of a lot of circles. So the first circle will be this whole thing, then the next circle will be something like this, and so on. I keep shrinking them down. So let me say F0 for the restriction of F2. So let's say this is the circle at time 0, and like you start shrinking it at time 0, and at time 1 you end up over here. So like at a general time t, this is what your circle will look like. So F0 is just F restricted to the time 0 circle, and in general if I look at Ft, it is F restricted to the time t circle. So I get a lot of maps from S1 to S1 by identifying each of these circles with S1, and I can find the winding number of each of them, right? So would you agree that as I do this sliding, the winding number stays constant? Think about it.
Yes, radius is decreasing.
Yeah.
Angle accordingly.
So also another way to think about it is that the winding number is always an integer, right? If somehow through this sliding the winding number changes at some point, it has to be a discontinuous jump because you're going from one integer to another. But this is like a continuous sliding, such a discontinuous jump cannot happen. Again, hand waving, but you sort of get the idea. So throughout this sliding, the winding number has to stay constant. But at time equal to 1, your circle is just like, your map is just constant map, right? Your circle is not going anywhere, winding number is obviously 0. So it's staying constant, and at the end it's 0, so at the beginning also it has to be 0. So that means, to summarize, if I have a map from S1 to S1 which also extends to a whole disk, then the winding number has to be 0, which explains why the winding number of each of these is 0. So N1 and N2 are 0, and that completes the proof, if you excuse all my hand waving. Thank you.